Alright guys, so we're going to do practice 3.10 together, and we're going to use these new motion equations that we learned to try to figure out these problems. Alright, so let's look at number 1 together. Marvin's motorcycle can accelerate at a rate of 4 meters per second squared when he starts from a stop. He accelerates for 8 seconds. Calculate his final speed. So before we get started, I want to let you know that this is a video for a reason, so you can pause and work on it on your own at any point. So if I go too fast, just make sure you pause. You can even rewind. Go at your own pace. Alright, so I put this guess method down here because I know that helps a lot of you, and so I'm going to follow that. If this helps you, go ahead and write out those letters as well on your paper. Alright, G stands for givens. What does the problem provide to us? It tells us he accelerates at a rate of 4 meters per second squared. So right away, it gives us the acceleration. Acceleration equals 4 meters per second squared. When he starts from a stop, he accelerates for 8 seconds. So it tells us the amount of time also. The amount of time he accelerates is 8 seconds. Calculate his final speed. So at first, it looks like that's all they give us. But there's something kind of hidden in this problem. It says he starts from a stop. Well, if he is stopped, we know his velocity is 0. Since they say that's the velocity he starts with, that's what's called velocity initial. V with a little I below it. His velocity initial is 0. He was stopped. A little hidden given in the problem. Alright, U. Unknown. What does the problem want us to find? It asks us to find his final speed. That is, his final velocity. That's what we don't know. E. What equation are you going to use to find that? Well, motion equation number 1 is an equation for final velocity. So let's write that out. Velocity final equals velocity initial plus acceleration multiplied by time. That's the equation we want to use. Okay, the S stands for substitute. What that means is we know what some of these values are. We know acceleration, we know time, and we know velocity initial. We're going to plug in these numbers into the appropriate spot in our equation. So velocity final will equal, our velocity initial is 0. So I'm plugging in that 0 where velocity initial would be. Okay? Plus acceleration, which over here in our givens we know is 4. So I'm going to put in a 4 for acceleration, multiplied by the amount of time. And the amount of time in this problem is 8. So 4 times 8 will give us that final answer, because adding 0 to it is not going to change it. So 4 times 8, most of you should be able to do that in your head, gives you a final velocity of 32. Don't forget, you do need a label. So 32 meters per second. So I worked this entire problem out with you. I'm not going to work every problem out with you in full length, but this one I did just to get us started. So 32 meters per second. Alright, let's look at the next part. Using this information, generate a table of position and time data for the 8-second period, calculating delta x every second. Use the table below. Alright, so what it wants us to do is for those 8 seconds that it moves, fill in this data table and graph. So what I'm going to do is make this data table a time and position table. And it wants us to do this for the 8 seconds. So we'll start with a time of 0, and every second up until 8, we'll find the position that this is at. Alright, so to do that, we have an equation to give us distance. And I'm going to write it out up here. Distance, motion equation number 2, is velocity initial multiplied by time plus 1/2 acceleration multiplied by time squared. Great, so this is the same problem as before. If you remember, earlier we said that the velocity initial was 0. He started from a stop. What's nice about that, guys, is if this is 0, it doesn't matter how long the time is, this is just going to go away. 0 multiplied by anything is just 0. So we only have this half of the equation left. Alright, so let's start to fill in things here. So what we have left, delta x is equal to 1/2 of a. Well, looking back at the problem, let's look back a little bit. Remember, that was given, a was 4. So in my head, I can just think about this really quick. Half of 4 would be 2. So rather than writing 1/2 times 4, I'm just going to write 2 because I know half of 4 is 2. Okay, we're multiplying this by our time squared. Alright, so we went from this long equation, velocity initial is times time plus 1/2 at squared, and we ended up with just this. This is what we're going to use to finish the rest of our data table. So all you'll need to do is take whatever time you're working with, so the first one would be 0, and plug it in right here. Well, 0 is really easy. We know that if we are using 0, 0 squared is just 0, and 0 times 2 is still 0. Delta x will be 0. At a time of 0, he hasn't moved at all. Alright, now let's try a time of 1. I'm actually going to plug this in to show you what it looks like. So for a time of 1, delta x will equal 2 times that time of 1 squared. Alright, so our first step is to square the 1. When you square 1, your answer is still just 1. So then you have 1 times 2. So that will give you a final answer of 2. Okay, you continue this with each of the other times. I'll do one more with you and then I'll let you get going. So the next one, we have a time of 2. So we're plugging that in for delta t. Delta x equals 2 times our time of 2, but then we have to square this. Okay, so 2 squared is 4. I'm going to write that out. So 2 squared gives us 4. 4 times 2 gives us our final answer for that one, which is 8. Okay, so I know that at a time of 2, it's at a position of 8. Alright, I'm going to let you do the rest. Remember, all you need to do is square whatever time you have. So the next one you'll take 3 squared, and then you'll double that. You'll multiply it by 2. Finish that data table. Then you'll need to scale your axes and plot those points over here. Okay? Don't forget to put labels for position and time. The last part, part D, is very simple. You'll just need to make a motion diagram to show that type of motion. You guys are good at those. Alright, looking forward, problem 2. One morning my car was accelerating at a rate of 3.6 meters per second squared, and after 6 seconds I was at a speed of 92 meters per second. What was my initial speed? Interesting. Alright, so givens. Let's write those. My car was accelerating at a rate of 3.6, so our acceleration equals 3.6 meters per second squared. After 6 seconds, so that's our time, delta t equals 6, I was at a speed of 92 meters per second. So what it's telling us is that's the final speed that they reached, the final velocity. 92 meters per second. What was my initial speed? So in this case, we know the final. What we don't know is the initial. We're using VI. We're trying to find out what that is. Okay, so now we have to decide what equation will we use to find VI. The problem is, out of our equations, we don't have one that is already solved for VI. But look what we're working with. We have an A, a delta T, a VF, and a VI. We have all those same variables in motion equation number 1. Motion equation number 1 looks like this. Now this is not an equation for VI, but watch. We know what A is, so we have this. We know what delta T is, we have this. And we know what VF is, we have that. The only thing we don't know is VI. So we can use this equation and solve to find out what VI is. That's what we're going to do. So let's do the next step. Let's substitute the numbers we know into this equation. So VF is 92. So we have 92 is equal to VI, which we don't know, so I'm just leaving that as VI, plus acceleration, which we know is 3.6, multiplied by the amount of time, which is 6. Alright, the rest I'm leaving you to solve. So your next step will be to multiply those two together, multiply 3.6 times 6. Once you've done that, to get VI by itself, you'll just need to subtract that from 92. So you'll get a final answer for velocity initial, and just be sure to put a label for the units there. Alright, number 3. A bowling ball slows down. So this is something slowing down due to friction at a rate of 1.2 meters per second squared. 5 seconds after it starts to slow down, the bowling alley, 5 seconds after it starts down the bowling alley, its speed is 15 meters per second. What was its initial speed? Alright, so givens. The first number it lists is this 1.2 meters per second. So that's our acceleration. Here's what's important, guys. This is something slowing down. In a problem like this, a calculation type problem, if something is slowing down, the acceleration will be negative. So even though it's not listed in the problem as a negative, the acceleration is a negative 1.2 meters per second squared, just because the object is slowing down. The next thing, delta t, is 5 seconds, the amount of time. And it tells us that it slows down to a speed of 15 meters per second. That's our final velocity. The unknown, what they ask us for, is initial speed. What speed did it start with? They're asking for VI. Alright, so I'm not going to do any more of this problem with you because this looks a lot like the last problem we just did. We know acceleration, we know time, we know final velocity. We're solving to find out what VI is. So if you need help on how to set this up and solve, look back to your last problem, problem number 2. It was the same setup. In the end, you'll end up with a velocity initial that the ball was thrown with. Okay, and then for the last problem. The last part of this problem, we're still talking about that bowling ball, but we're wanting to draw a table and graph what the bowling ball's motion looks like. So just like we did on the front page, we're going to have a time column and a position column, or distance. Okay. Now it tells us in the problem that this ball is only going for 5 seconds. So we're actually not even going to use this entire table. We're going to start with a time of 0 and only go to a time of 5 seconds. That's as long as it moves. So we don't need these bottom 3 boxes. We want to find out at each second what position is the bowling ball at. Okay, so at a time of 0, it has a position of 0. We know that's going to be the case. To find out the other ones, Once again, we're going to have to use motion equation number 2. Remember, it's the longer one. Delta x equals vi times delta t plus 1/2 acceleration times time squared. So we can do this a lot like we did the front page, except this one, we do have a velocity initial. This first half of the equation on the front page, we just canceled it out because velocity initial was 0. We can't do that this time. In this problem, our velocity initial is whatever answer you got on part A. Okay, so this one is the challenge half of the problem. I want to see how you do. So remember, we have a negative acceleration and we do have a velocity initial. So you'll plug in the times for each section and see what position the bowling ball should be at. Okay, I hope you guys do well. Make sure after you graph the bowling ball's motion that you make a motion diagram, and that'll be it for the day. Good luck.